is, in the last class we have seen what are the content of the syllabus which we are going to see in this particular semester. So chapter 1 is mathematical modeling of physical systems. Especially we are going to consider mechanical system, electrical system, electromechanical system at most, and then we are trying to obtain transfer function of those systems. And chapter number 2 is, once the system model is ready, then when you apply input signal, how the system is going to behave is what we are going to simulate with the help of standard test signals like step signal, ramp signal, and parabolic signal. And then once you have the response analysis, once you apply the input, then how the system is going to behave, we are going to see we are going to divide that into transient response and steady state response, and then with the help of few characteristic parameters, we are going to describe the behavior of the system. Right, up to that particular point is what we have seen. Right. So now the next part is the unit number 3, which is stability analysis. So what do you mean by stability? Now, stability point of view, we talk about BIBO. We heard about word BIBO?
Yes, sir. Bounded input.
What is that? Bounded input? Bounded output. Means what? If you give a finite input, you should get finite output. You should not get infinite output. Is it not? Yeah. So in that case, few systems, when you apply finite input, you should get finite output. Do you have anything in mind? When you give finite input, do you get infinite output? Do you list any device which you come across your experience which gives for a finite input which gives infinite output? Example, I'll tell you, see, this is a spring, right? Right. So now you apply a force F of t and then leave. What happens? It oscillates, and after sometimes the oscillations are going to die out, right? Yes or no?
Yes, sir.
So for finite input, for finite means, for finite output you get, and then you get. But the other way is what? For finite input, you should get infinite output. Do you have any such cases which you came across? Yeah, let me give an example. There is a transfer function. Let us take one example. 1 by 1 plus s is one transfer function. And there is one more transfer function which is 1 by 1 minus s. Right? Okay. So now if you want to see the time domain response or time response analysis, then you would be you would be doing what you need to do if you want to. Now this is in S domain, right? If you want to get a time response analysis, what you would be doing?
Inverse Laplace transform. We'll apply inverse Laplace transform.
Will apply inverse Laplace transform. Correct. Right. So now tell me, inverse Laplace transform of this is what?
E power minus t.
So this is e power minus t. So this particular system, okay, which can be a ratio of Laplace transform of output by Laplace transform of input. Okay, so input, if it is an impulse, Laplace transform of impulse is 1, and then we are going to get C of t here. Okay, right. Okay, this is C of t. What would be the case here?
E power t.
E power t. Right. Now, if you try to plot the response of this particular system, right, C of t versus t, right. So when t tends to infinity, what happens here? E power minus t case, e power t case.
E power minus t approaches 0.
So e power minus t, it approaches 0. And what happens to e power t?
It approaches infinity.
It approaches infinity. So for finite input, you are going to get finite output or infinite output. Exponential output is what you are going to get, right? In this case, right? See, we give an input of 1, but there is an exponential increase, is it not? So coming to the third chapter, what we are going to see is whether a system is stable or unstable is what we are going to see with the help of stability analysis, which is bounded input and bounded output test. So so what we'd be going to do is we are going to see the stability analysis. So we will be using two techniques. One technique is called RH criterion. Okay, we will be using RH criterion. See here, now if I try to plot this on the S plane, there is a pole lying on the left half of the S plane at -1. And here there is a pole which is, we are going to see what those and all. There is a pole on the right half of the S plane. So when there is a pole on the left half of the S plane, then we are going to get response like this. But when there is a pole on the right, then we are going to get a response like this. So the reference is imaginary axis. So if you take this is a S plane, so this is real part and then this is imaginary part. Okay, so if you have if you transfer function, if the poles are lying on the left half of the S plane, the system is said to be stable. And if the poles are lying on the right half of the S plane, the system is said to be unstable. So those criterion without solving the characteristic equation. So now let us take, you have a transfer function, and then the transfer function is of having a sixth order polynomial. Sixth order means s bar 6 plus 6, s bar 5 plus so on and all. It becomes very difficult to find out the roots, right? Yes or no?
Yes, sir.
Yes, sir.
In that case, what we do is without solving the characteristic equation, we will say how many number of poles are lying on the left half of the S plane, how many number of poles are lying on the right half of the S plane with the help of a criterion called RH criterion, Routh-Hurwitz criterion. So that is what we are going to see in the third chapter. But this RH criterion, few systems now, if you try to take this, you can consider this as a system. Okay, this is one particular system. A ball is placed here. Okay, there is one more system where the ball is placed here. There is like this kind of system. There is one more system which can be of this kind. Right. So here without applying any we cannot make this system stable. The ball always rolls down. Okay. So the system is unstable. And here how much force you apply also, this is so deep you cannot take it out, then the system is called stable, completely stable. Right. So now when you apply force, because of the shape of the system, it is like this. Up to certain force, the system is stable, but after that the ball will come out of this. The system is called conditionally stable. So in stability also we have three terms, 3 to 4 terms. One is unstable, stable, conditionally stable, marginally stable. There are 4 words related to this. marginally stable. So all the stability criterion we may not, or we will not get by using RH criterion. Then we use one more technique called root locus technique. Okay, we will be using a technique called root locus technique. Okay, and using the root locus technique, we will say the system is stable or unstable. So before our objective is what? When a system is there, we need to control it. So controller design is what we need to do. But unstable system you cannot control. So first thing is uncontrolled system, unstable system, you have to make it stable. Then you have to design a controller for it. This is what the sequence. Right. So the root locus is one particular technique, is a picture graphical technique by which you can say a system is stable or a system is unstable. All right. Then there is one more technique called Bode plot. Right, Bode plot. There is one more technique called Nyquist plot. So this all will give you same similar. The system is stable or unstable or conditionally stable or marginally stable. So chapter number 3, we would be seeing this. All right. Now, chapter number 4. So now I have a system like this. Right. So when I applied input of a system, the output is, this is what the input. Okay. So this is what input. Okay. And this is what output. So this is what output. Right. So there is a system. When I excited that system with input, the system, you are getting response like this. So here now, let us take the same example, DC motor case. Right. So there is an DC motor, right, which is attached to a shaft. So the moment I switch on the motor, the rotor has to achieve a RPM, okay, RPM of 1500. Okay, 1500 RPM is what it has to achieve. Okay, right. But now this 1500 RPM is achieved in 5 minutes. The system is slow. Train you have seen, right? When it stops, then it has to pick up the speed in as soon as within the less time. Correct? Yes or no? Yeah.
Yes, sir.
So, yeah. So in that case, system performance need to be improved. Means transient response and steady state response need to be improved. And now a system is given, is having a response like this. Okay. And one more system is having a response like this. Okay. One more system is having a response like this. And there is one more response is, one more system is having a response like this. Right? So the red color one is system 1. This orange color one is system 2. Black color one is system 3. So which system is behaving quickly? The moment I give input, right? So this is what, if you consider this as 100% output. So here this is taking, let us take 10 seconds to reach 100%. But this is taking 5 seconds, right? and this is taking 2 seconds to reach 100% of the final value. So out of these three, which one is better?
Third, 2 seconds in 100%.
Yeah, so yeah, that means what? Within no time, you should get your output, right? The moment you give input, you should get output. So this kind of thing, so we say it as improving the steady state. It means transient response and steady state response, right? So here there are certain peaks, some error is there, but there would be one more system which could be like this. There is no peak and all, right? So improving the steady state response and improving the transient response of a system, we try to do with the help of we design controllers, right? So we design controllers, right? We design controllers, and controller design is what we are going to see in chapter number 4. So chapter number 4 is about improving the behavior of the system by designing controller, or we can call it as there are two kind of systems we can design. One is compensator and another one is controller. The widely used controller is PID controller, proportional integral derivative controller. 80% of industrial controllers are PID. And there are few controllers are there like compensators, like lead compensator, lag compensator, lead lag compensator. Right. So using some compensation techniques, we improve the behavior of the systems. That is what we are going to see in 4th chapter. Right. So that is about chapter number 4. And coming to chapter number 5. So the system when we are trying to take, right, the systems which we are trying to take up to now, we make certain assumptions. One assumption is the system is linear. What do you mean by system linear? Anyone define linearity? Because you have undergone the course signals and systems. Linearity. Resistor is linear or non-linear device?
Linear.
How do you say it is linear? Try to apply voltage across it. The current is proportional to input, right?
Yes, sir.
Is it not? Yeah. So resistor is linear device is what? I just gave an example, but tell me the definition of linearity.
Slow.
Huh?
Superimposition should be like two signals.
Very good, Shakil. When a system is linear means it has to obey superposition. Principle of superposition. So what do you mean by principle of superposition?
So it's proportional, and also it's like if we multiply with two, if we multiply the equation with the two different constants, and we can add it just like.
So proportionality and homogeneity. Okay. A system to be linear means it has to follow these things. Superposition theorem and homogeneity is what it has to follow. Right. Okay. So the system which we considered up to now, the first assumption is the system is linear. But are the real-time systems are linear? Are the real-time systems are linear? Transistor is linear device or non-linear device?
Non-linear.
Non-linear device. But we are assuming that transistor is linear, or piecewise linear characteristics is what we are drawing, right?
Yes, sir.
So the assumptions when we try to take the system is linear. And we say that system is time invariant. What do you mean by time invariant?
If the characteristics are fixed over a period of time, then we say the system is.
Example?
Mm,
Okay. Now I am buying a brand new car which can go a maximum speed of 180 kilometers per hour. Right. So first year, the performance was designed is 180, but maximum it got 170. Okay. After some time, after let us take 5 years, do you get the same speed with the same car?
No, sir.
No, sir.
No. So the system is time invariant or time varying. Here, the behavior of the system is with respect to time, the system is varying or invariant.
Varying, sir.
So the real-time systems are invariant. Okay. Okay. Yeah. So now tell me. So time invariant means we assume that system is not changing with respect to time, but all real-time systems are changing with respect to time. So the assumption is when the system is linear time invariant system, then only we can apply Laplace transform. Is it not?
LTI systems. Yes, sir.
LTI systems. So the model which we did up to now is using what?
try.
Transfer function. So transfer function is what? Laplace transform of output by
Laplace transform of input.
Laplace transform of input. Right. So, but all real-time systems are linear time varying systems. When they are linear time varying system, the modeling is done by using integral differential equations. The system is modeled by using vector matrix differential equation. Vector matrix differential equation, and which we call it as state space representation. State space representation. So here what we do, the entire system in time domain we will model, which will take care of the non-linearity also, time varying behavior also. So x dot of t is equal to ax of t plus bu of t, and y of t is equal to cx of t plus du of t. So any physical system we will model in the form of vector matrix differential equations. So that particular topic is taken care in chapter number So what is chapter number 5? Representing the system in state space form.
So in this, in here we are just splitting the time into small parts where it is time invariant.
Time varying systems also we will consider here. The
No,
modeling
sir,
here,
like-
what we have done is in frequency domain. Means, the model which we got is in frequency domain. Okay.
Yes, sir.
But here we will try to represent the system in time domain itself. Okay.
Yes.
Right. So we will see. We will see. So the chapter number 5 is modeling the system in state space representation. So I want input y of t. So I want the output y of t. But y of t can be known when you know x of t. But the real-time systems are available in the form of differential terms. Is it not? When you try to apply KVL, the equation which you get, integral differential equation, is right is in terms of differential form, and then mechanical system are also governed by second order differential equation and so on. In that case, the system states are not directly known, they are available in terms of differential terms. So what we do is, solving nth order differential equation is very difficult. So what we do, nth order differential equations, we try to represent that as n first order differential equations. And we call it as state space form. And now that is available in terms of matrix. The moment the system available in the form of matrix, there are so many number of softwares available like MATLAB, which stands for Matrix Laboratory, which easily analyzes the system and gives the response instantaneously. That is one advantage of state space representation. Okay, more in detail is what we are going to see in coming classes. So in chapter number 5, what we are going to do is, we are going to represent the system in terms of state space representation form. And we have to know, the moment you give input, the output is what you have to get. What do you mean by this output and all? So now let us take, there is a RLC system. Now you are applying a voltage V of t. How the current is flowing in the circuit is what I want to know. I applied a voltage, and then here I am connecting one voltmeter which reads the voltage across the capacitor. But I want to know the current. So few variables are observable or measurable. Few variables are not observable. They are intermediate variables. Right. So then what we do is, we have to get the output. The moment you get all the states of this, so then you need to solve the vector matrix differential equation. So how to solve this vector matrix differential equation? The solution of vector matrix differential equation is what we are trying to say. So solution of vector matrix differential equation is what we are going to see afterwards. Once we model the system in state space, then we try to see the solution of it. And when it is represented, then we have to get the same thing, like how the system behaves, whether the system is stable or not. So then we will be seeing observability, okay, and then controllability, by which we can say the stability of the system. So these concepts and all we are studying in chapter number 5. So the syllabus of control system is like this. We start with mathematical modeling of the system. Then we do analyze the system by applying input. Then we characterize the system. And once the system characteristics or behavior is not that much as we require, then we design controller right? We design controller and then we try to see the response of the system. At the same time, we will analyze the system behavior and all, right? Stability of the system and all. Then, the real-time system, how to handle is what just introduction is what we try to see in chapter number 5 in terms of state space representation. And then at master's level, if you try to do your course, and you will be seeing the analysis and rest of the parts and all. So this is about syllabus of control systems. The good books are automatic control system by uh, automatic Benjamin C. Kuo is what the textbook. Parallelly, you can follow modern control theory by Ogata, and very nice book is Control Systems by NICE, N-I-C-E, NICE. Okay, so these books you can follow. And examination pattern, anyhow, So mid-semester examination will be for 30 marks, and end semester examination is for 40 marks. And assignment, I will be keeping and 1 or 2 assignments, which is objective type. So the assignment, that will be taken care. So every semester is of 14 weeks, 16 weeks actually, 2 weeks for examination. So 14 into 3, 42 hours we will be interacting. I think almost this is 4th hour, right? So we'll be interacting. So 42 hours we'll be interacting, and 1 week for mid examination and 1 week for your end examination. So 16 weeks a semester. Right. Do you have any questions, please, regarding the course and delivery and evaluation pattern? Do you have any question?
Could you repeat the names of the textbooks?
Yes.
Automatic Control Systems by Benjamin C. Kuo. Okay. And Modern Control Theory by Ogata. And Control Systems by NICE. NICE book is really very nice. And these are
Any
available.
one book is enough, right, sir?
Why one book is enough? Tell me.
No, just for like flow, sir, like that.
See, I think I do have those things. Different authors will be having different perspectives. One book will be dealing more theory, and one book would be dealing the realistic situations. Right. So the nice book, that really deals with all. It takes real-time cases. How aeroplane control is done, and also realistically, if somebody is talking, that will be dragging your interest. So nice will do the analysis of the real-time systems, and then you will be achieving or arriving to a conclusion. So in that particular practical oriented book is nice. Theoretical is okay. That is cool. So different authors' perspective would be different. Okay, so that's why we need to follow. Tell me. Any other questions, please? So this is what the course plan. Okay, so I think around 42 hours. Yeah. So introduction to control systems, components of control systems, open loop and closed loop control systems, and system differential equation, mathematical modeling of mechanical and electrical systems, analogy, tutorials, so on. Okay. Any questions, please? If you have any questions, you please let me know, or otherwise we will be getting into the content. Do you have any questions, or shall we go ahead?
We shall go ahead, sir.
Let us go ahead with open loop and closed loop control systems. System means an interconnection of elements and devices for a desired purpose. Control system is an interconnection of components forming a system, a configuration that will provide a desired response. Now, so coming to the systems, there are open loop systems and closed loop systems. Right. So open loop system, you will be having a block diagram like this. So now let us try to take this particular example. This is a missile launcher system, right? So you will be at some remote location, and now you have to launch the missile so that it exactly hits the target. But let us take the target is changing. So you fix it at some, let us take 40-45 degrees. But when target is changing same 45 degrees, if you fire missile, that is going to be waste. So where there is no relationship or output and input, there is no interaction, those systems are called open loop systems. And now, by seeing the output, that means you will be seeing the output and then changing your firing angle. So here desired angle is, let us take 45 degrees, right? But now as the target is changing, then your firing angle would be different. So the actual position of this and the desired position of this, so that you will be getting an error, and then you will be firing a missile. So this is called closed loop control system. Closed loop control system. So open loop control system, one more example is air conditioning system. AC. Air conditioning system, what you do to have an AC. So in winter, in summer, and then in summer, generally what you do, you will be keeping your room temperature at a particular like 20 or 24 degrees centigrade, right? So it is an open loop system, but there would be an AC which is an intelligence in the sense what, which exactly knows the temperature of the system, and if it room, and then if it is more than, let us take it is 26 degrees, then it start working, and if it is less than 26 degrees, like it is 24 degrees, then it is stop working. That is how you can save power. They are called intelligent, right? The intelligent means the output, which is a required temperature, is what you are taking into consideration and then working accordingly. And those kind of systems are called feedback systems or closed loop systems. Systems would be open loop or closed loop. Examples are so many. Right. So now let us take, this is one more example. There is a tank. The objective here is there is inflow in the tank, but some chemical reaction is what happening in the tank. So now the liquid level of the tank has to be made constant. Okay, the liquid level of the tank has to be made constant. All right. So now here there should be an observer who sees the level of the liquid, and when it is above the level, then he just opens the valve so that the liquid will be going out of. And if it is less, then he closes the valve so that the liquid will be at constant level, right? So this is called open loop system, right? Okay, so automatic, now this is what your same example which I am saying, right? So there is an outflow, there is inflow, opening and of closing. So this is open loop system. It has to be closed loop system, means what we'll be doing is we will be measuring the liquid level by using some sensors, level sensors, and we have a desired level of the liquid in the tank. Okay, desired level in the tank. Then actual level is what we try to compare. If there is an error, then opening of the valve or closing of the valve is done by the controller. So where you are trying to take the reference, your reference, and then making opening or closing. So the visual linkage here is with the help of human, and the same thing can be performed by machine. So it is called feedback control. Is it all right? So open loop systems and closed loop systems. One more example. You want to drive your car with 70 kilometers per hour. So you are applying pressure on the pedal so that you are going with 70 kilometers per hour on the road. But if there is a speed breaker, do you go with 70 kilometers per hour? No. If you don't have a visual linkage of your speedometer and your eyes, so your brain is a controller at that particular time. So you are trying to set the speed, which is my output quantity, which I want to maintain it at 70 kilometers per hour. So if there is no visual linkage, then applying some pressure, and the system goes with some particular response. But there is a disturbance in between. You will not get the achieved or desired output. Is it not? So out means open loop systems. The response is what we will not get the desired one when there is a disturbance. But whereas there is a closed loop system or feedback system, when we are seeing the speed is less than 70, it is somewhere around 50 kilometers per hour, then we increase the pressure on the pedal, and then the speed of the car will be increasing. Is it all right? So open loop systems and closed loop systems. So this is open loop system. So there is this is closed loop system. So the real-time systems and the control systems which we are going to consider are closed loop systems. The input is called set point. The output is called controlled variable C of t. Laplace transform of it is C of s. This is desired input or reference input, which is called R of t, reference. Laplace transform of this is called R of s. And to compare your input and output, there should be a comparator. And then this is what your processor planned. Okay, this is what your processor planned, and we design a controller to achieve desired response. The more details we will be discussing in the next class. Okay, So open loop system, closed loop system, a reference input, controlled output. Okay. So now if you try to see in this particular example, right? So what is the objective here? What is the objective? To maintain liquid level to a constant, right?
Yes, sir.
Constant height. So liquid level height. So here, what is the controlled variable here? Liquid level. Correct? No. Right? And what is the input here? Desired level or reference level, right? The liquid in the tank can be of, let us take, 50 centimeters or 100 centimeters and so on. So that is desired level. This is output is what liquid level means. Level of the liquid has to be maintained constant. This is desired and this is liquid. There are few terms related to this. So liquid level has to be maintained at certain level. Right. So we use some sensor to measure the liquid level. And here we try to compare actual level with reference level, right? Is it not? We compare the actual level with the, this is what the actual level, and this is what, so we'll be using some sensor here to measure it. And the sensor will transmit the signal from output to the control station. That's why the name transmitter. So it compares, okay, right, compares, then the output here, the thing here is manipulated variable. So what do you mean by manipulated variable here? So to maintain the liquid level to a constant level, the outflow is what we are, that means the valve is what we are opening or closing. So the outflow rate is what called manipulated variable here. Manipulated variable, outflow. We have to reduce it or we have to flow rate units. Flow rate.
Centimeter cube per second.
Meter cube per second. Okay. Meter cube per second. Right. So that is called manipulated variable. The variable which we are changing to control the output is called manipulated variable. Now, objective is to maintain the liquid level constant, but there is an inflow. Do you get inflow with same pressure with all the time?
No, sir.
No. We will be getting the liquid flow all of a sudden with different pressure and different volume may be released, right? So which changes the output. This is called disturbance. Understood? Disturbance, controlled variable, manipulated variable, set point, and all. Understood?
Yes, sir.
Right. So this is called closed loop. So you try to take any one particular control system and draw this kind of analysis. Okay, this is very, very important. Try to take a realistic control system and an example, and then try to see the set point or desired input, controlled variable, disturbance variable, manipulated variable, error, then sensor output. Okay. If you have any questions, please, by this time. Any questions, please? So what you do, you try to take realistic cases, and then if you come across anything. So my mail ID is jrkassignment. Okay, jrkassignment@gmail.com. So send me.
Sir, once
Okay,
you
if I
repeat
feel like any good system you are coming across, we'll be discussing in the next class. Okay. Vaibhav, you are talking something?
sorry, sir, accidentally mic on.
If you have any questions, I'll take up, or otherwise we'll be meeting in the next class. Thank you.